we're going to look at 5.5, zeros of polynomials. We're going to start to look at complex zeros, which means zeros that are possibly not real. Let's look at this example. We have a polynomial function. We're given a 0 of 3, and we want to find the other zeros. So we learned how to do this in the previous section. We are going to use synthetic division, and we put our 0 in that position, and then we write out our coefficients and go through the synthetic division. Bring down the 1, multiply by 3, we add down and get 0. 0 times 3 is 0, add down, we get 16. 16 times 3, we get positive 48. We add that down and we get 0, which is the remainder, and that's what we would expect because x equal to 3 is a 0. So remember that means f of 3 equals 0, which just confirms that 3 is 0. Okay, so that's great. We were told that. We just confirmed it. This is the real result of the synthetic division. It gives us the coefficients of the other factor. So now we can write our polynomial in partially factored form. We have our factor x minus 3, all right, which comes from x equal to 3 being 0. And now the other factor is x squared, 1x squared plus 16. So x squared plus 16 is our other factor. Okay, so we want to use this x squared plus 16 to find our other zeros. So to do that, we set that equal to 0, and now we want to solve for x. So we subtract x from, or 16 from both sides. So we get x squared equals negative 16. And we know what to do. We take the square root of both sides, remembering our plus or minus, and we end up with x equal to plus or minus the square root of negative 16. All right, we have that dreaded negative number underneath the square root, and we have been saying all semester that that is not a real number. Okay, we got to be able to deal with this. So we're now going to just take a quick break, and we're going to switch to talking about not real numbers, or what we call imaginary numbers. Okay, so to talk about complex numbers, we first have to talk about this square root of negative 1. Okay, well, we've already established that it's not real, but it is something that we have to kind of encounter often in different kinds of problems. So we have a symbol that stands for the square root of negative 1, and that is the lowercase I. And we call that the imaginary unit. All right, we want to use that to rewrite any time that we have a negative under the square root. So let's say we have the square root of negative 5. Well, we want to use the imaginary unit instead of having that negative. So think about how we can factor underneath the square root, and we could factor that into 5 times negative 1. Okay, I is equal to square root of negative 1, so we can rewrite this as the square root of 5 and replace this square root negative 1 with I. All right, so instead of having a negative under the square root, we use that I to represent the square root of negative 1. Okay, let's look at another example. Let's say we have the square root of negative 9. Okay, again, we want to write it so we don't have a negative under the square root. We want to use that imaginary unit. So again, we can think about factoring that negative 9 to just 9 and negative 1. Well, square root of 9, that simplifies to a 3. We can replace the square root negative 1 with I. And so square root negative 9 is just simply 3I. All right, let's look at another example. Let's say we have the square root of negative 20. Okay, well, let's think about how we can factor that. So we can factor that as square root 20. square root negative 1. We can replace the square root negative 1 with I. And then also we want to simplify that square root 20, so we can write that as 4 times 5. And the square root of 4 simplifies to 2, so we get 2 square root 5i. Okay, so these are all examples of imaginary numbers. So whenever we have I, we have an imaginary number. Now sometimes we have a combination of real and imaginary. So for example, if we could have 7 plus 2i. So this number has two parts. It has the real part, which is just 7, and it has the imaginary part, the 2i, the part that has the I in it. Okay, so when we have a number that has a real and imaginary part, we call that a complex number. Okay, so here's a definition of complex numbers. They have a real part and an imaginary part. So in general, we can say an imaginary number can be written as a plus bi. Okay, so real, imaginary. Okay, let's look at an example. I want to take 2 plus 3i and multiply that by another imaginary number, 2 minus 3i. Okay, so you notice that they have the same real part and they have the same imaginary part. Okay, when we have two complex numbers that have the same real and imaginary part and they're only different by the plus or minus in between, we call those complex conjugates. Okay, and I think I misspelled. Let's try that again. There we go. So let's see what happens when we multiply these complex conjugates. So we are going to actually do this by FOIL. All right, you see how we have two things combined with addition and subtraction in those parentheses. So that means that we can multiply using FOIL. So first times first, we get 2 times 2, we get 4. Outer times outer, we get 2 times negative 3i, so that's negative 6i. Inner times inner, we're going to get plus 6i. And last times last, we get negative 9. I times I, which is I squared. Okay, so we can see that the negative 6i and positive 6i cancel each other out, so we are left with 4 minus 9. Let's look and think about what I squared is. So I squared is square root negative 1 times square root negative 1. So when we square a square root, it just undoes that squaring. So that's we're left with negative 1. So that I squared equals negative 1. So we end up with 4. Negative 9 times negative 1 is plus 9. So 4 plus 9, and we get 13. So when we multiply the complex conjugates, the imaginary part goes away, and we're just left with a real part. So we can simplify this to say that when we multiply complex conjugates, a plus bi times a minus bi, that's always going to result in a squared plus b squared. Okay, one more thing before we get back to our example. Non-real zeros to polynomial functions always occur in conjugate pairs. Okay, so we never get just one non-real zero. We're always going to get two if we have one. Okay, so getting back to our example, f of x equals x minus 3 times x squared plus 16. We got down to this solution of x equals plus or minus square root of negative 16. We now know that we can rewrite that using the imaginary unit. So we can rewrite that as square root 16 times the square root negative 1. And then simplify that square root 16 as 4 and rewrite that square root negative 1 as I. So we get two imaginary zeros, x equals 4i, x equals negative 4i. And these are complex numbers that just happen to have the real part being 0. Okay, let's look at this example. We have a polynomial function. We're given a 0 of negative 2, and we want to find the others, real and not real. So we're going to use our synthetic division, set this up. So bring down that 1, multiply by the negative 2, add down, multiply, add down, multiply, add down, and we get 0, which is what we would expect. That confirms that negative 2 is a 0. And this gives us the coefficients of the other factor. And we can write our polynomial in partially factored form. So x equal to negative 2 gives us a factor of x plus 2. And then using those coefficients, right, we're going to have x squared minus x plus 3. So we get x squared minus x plus 3. Okay, so we want to use this quadratic to find the other zeros. And so far we've been able to factor. But if we give this a try, x and x, and we try to find it two numbers that multiply to 3 and add to negative 1, we are not going to find them. So that does not work. So think about what we're doing. We are solving this, x squared minus x plus 3 equal to 0. What's our other tool that we have besides factoring? Well, we can use the quadratic formula. So x equals negative 1, so that's a 1, plus or minus 1 squared minus 4 times a times c, so 4 times 1 times 3, so that's 12, all over 2 times a. All right, so you are simplifying, and we have a negative 11 underneath the square root. So we get some complex solutions. Of course, we do not want to leave that negative in the square root, so we're going to rewrite that as 1 plus or minus square root 11i all over 2. Now, if you want to write this so it looks like it has the real part and the imaginary part, we can write the 1 over the 2 and have 1/2 plus or minus, and then write the 11 square root of 11i over 2. So you can see that we have two complex zeros in conjugate pairs. So we have the 1 is 1/2 plus square root 11i over 2, and the other one is 1/2 minus square root 11i over 2. Okay, here's another example. I would suggest you give this one a try on your own and then restart the video and see if you match up with what the video shows. So we're wanting to find the other zeros given that 2 is a 0. So set up our synthetic division, plug in those coefficients, and now run through the synthetic division. So we'll bring down the 1, multiply by the 2, add down, multiply, add down, and then multiply, and we add down and get 0, which confirms that x equal to 2 is a 0. And that also tells us that x minus 2 is a factor. And then we can get the coefficients of the other factors from these numbers right here. So 1x squared minus 6x plus 13. That's going to be our other factor. And we can try to factor that. All right, we're wanting to find the zeros that come from that factor. So we set it equal to 0. We can try to factor, but we're not going to find two numbers that multiply to, this one, 13 and add to negative 6. That's just not going to work. So we are going to need to use quadratic formula again. So x equals 6 plus or minus the square root of negative 6 squared, which is 36, minus 4 times 13, which is 52, all over 2 times a, so 2. So doing a little bit of simplifying, 6 plus or minus, we do that subtraction underneath the square root. We're going to get a negative 16, and then that's all over 2. All right, so we have a negative under the square root. We're going to get some complex zeros here. We want to rewrite that using I instead of a negative under the square root. So we can write that as square root 16 times square root negative 1. And square root 16 will simplify to 4. And square root negative 1 we can write as I. Now, we want to simplify as much as possible. So remember, first of all, we can write this in the real part and the imaginary part. We take the 6 over the 2, so 6 over 2, plus or minus, and then also take the plus or minus 4r, or the 4i over 2, so 4i over 2. And we can see how the 6 over 2 will simplify to 3. And the 4i over 2 will simplify to 2i. Okay, so the other zeros that we just found are x equal to 3 plus 2i, x equal 3 minus 2i.